let's look at something that's a little bit more complicated than this. I'm going to run out of space. Can I erase this stuff now, or do people still want to? Okay. The important things to remember are these prefixes and names, because we're going to use them again. So that is important to know. Okay. So now I'm going to ask a question. There's a unit of measure that we will use in this class called a light year. People heard of a light year before? What is it, the definition of a light year? What's that? First of all, what does a light year measure?
Distance.
Measures distance. So when you hear year, the first thing you think of is what? Time, right? Year seems like time, but it's not. It's measuring a distance. Why? It's measuring a distance because a light year is defined as the distance light. Well, we're going to have to spend some time figuring out what that is. Travels in a year. Why? Because light always goes the same speed. In fact, it's the only thing we know that always goes the same speed. Every other phenomenon, thing, and object in the universe can travel at different speeds. Light always goes at one speed. Do you know what speed that is? It's a pretty fast speed. Now I have a sad thing to tell you about. We often call the speed of light the letter c. That's unfortunate, because that's not the same thing as centi, even though they're the same letter, right? So when you see c and the context is the speed of light, you can't just replace it with 10 to the minus 2, even though I just said you could do that, right? This now is referring to the speed of light. So the speed of light, which we call c, has a known value. It's been measured. And that value is 3 times 10 to the 8 meters every second. We're going to learn a lot about thinking about when I say something, how do I translate it into a mathematical sentence? Right? When I say I travel 3 times 10 to the 8 meters every second, this is how I write it mathematically, including that division. Right? You may not have realized division was in there, but it is. When I say meters in a second, that means meters divided into, the seconds are divided into the meter. That's what it is. So 3 times 10 to the 8, I could have written this out with 3 and 8 zeros behind it, but obviously that's a little bit unwieldy. So I write it this way. I use the fact that I'm writing out 8 generations. I have gone through 8 generations of rabbits now, so I'm up to, well, if you said this word, it would be 100 million. But that doesn't really give us a very good conception anyway, and it's much easier to write it like this. So I will start writing these things like this. You multiply this 3. I will often use x for multiplication. Sometimes I'll use a dot, unless I have an x, and then I'll try to be a little bit more clear. But if there's ever any doubt, just ask, and we'll try to make sure that everything's standard. Yeah?
So 300 million
meters every second. That's about the distance between here and the moon. So if you shine a flashlight up towards the moon, 1 second later, that light beam hits the moon. That's true. Startlingly, this is not what we're interested in. That's how far light travels in 1 second. We're interested in how far it travels in a year. How many seconds are in a year? Anyone know? Seconds per year. Yeah?
And I have a question, like it's just a general question, like who counted the speed of light?
Oh, that's a great question.
How is that even possible to like calculate?
This is something we can actually do here in this college if we want to. There's a lot of ways to do it. The easiest way to do it is to look at we know you're aware that light is a wave, right? Which means that it has properties where it's intense and then it sort of disappears, and then it's intense and then it disappears, right? Is everyone aware that that's sort of a property that light has, right? What you can do is you can take light that's the same, has the same sort of wave properties, and you can look at the situation that happens when they travel slightly different path lengths, and then see what they do with each other. And because that repetition is happening at a known rate, you can actually figure out, oh, I've traveled this far and it had to take this long. And you sort of back it out how fast. It's so fast that it takes some pretty delicate equipment, but we have it here, and it's possible to do. You can actually measure it in a physics lab, is where you would typically measure it. Yeah.
And what
Yeah.
And what do they mean by light? Like, what are they talking about? Are they talking about
We will definitely get into that.
sunlight or
Sunlight is one form, but light actually has a lot of forms, including forms that we don't often think about as light. Right? So we don't often think of radio waves or cell phone reception as light, but it is. We don't often think of ultraviolet as light, but it is. We don't think of X-rays as light, but they are. They're all different
And like the
forms of
sun
light.
is the only like natural light, right?
No, I wouldn't say that. Anything that has a temperature emits light. The sun happens to be huge and happens to be pretty warm, so it's the most noticeable. But you're emitting light right now. Everyone in this room is emitting light. Obviously, this is emitting light. You can argue over whether that's natural, but fire is natural. Certainly, it's emitting light. There's a lot of ways to get light. The sun happens to be the major source of it here on Earth.
No, but I'm just talking about like man-made produced, like the actual forms of like real light. Like if we didn't have any of these electronics around us or anything, like that would be like the forms of light that they're talking about, right?
Well, we're talking about anything that
Yeah.
behaves, really, a very good definition is anything that travels this speed is light. But this is a subject unto itself. There's an entire chapter in the book on it.
Yeah.
So absolutely, let's talk about it. But I don't think we can spend all of the time right now to discuss all the different forms. Suffice to say that there is a lot of different forms of light, and that it's basically everywhere all the time. It's impossible to get away from. Even if you make a vacuum, there's probably light inside of that somehow. Any other questions about this right now? Yeah.
No, I was going to attempt to answer how many seconds are in a year.
Oh, great. What's the answer?
I think 31,536,000.
Yes, that's correct. I remember it by saying 3 times 10 to the 7. That's a nice way to remember it. I don't need to remember the exact number. I just need to know an approximation. Remember, that's what we were talking about. So I actually remember that this is the case. 3 times 10 to the 7 seconds in a year is the number of seconds in a year. The other way we can say it is this is equal to, since they're equivalent, it's equal to 1, right? You divide one thing, but it's the same as the other thing, they're equal to 1. I can rewrite this by multiplying a year on both sides. I can write that sentence like this. It's the same mathematical sentence. 3 times 10 to the 7 seconds is equal to a year. Everyone see how that was mathematical? I had a division here. I multiplied year over year, year over year. Year showed up here, year canceled here. All right, 3 times 10 to the 7 seconds is a year. If I know that this is the speed of light and this is how long a year is, if I want to know the light year, I just take the speed, you call it c, and multiply by the time, you call it t, and that's going to be the distance. So if I did it for 1 second, I would take the speed, 3 times 10 to the 8, and multiply by the time, 1 second, and I would get 3 times 10 to the 8 meters, the distance between here and the moon. But I want to do a light year. So I'm going to take the speed, which is 3 times 10 to the 8 meters per second. Always bring your units along. I'm going to multiply by the number of seconds, 3 times 10 to the 7. And that should be a light year.
Wait, what does
c is the speed of light. That's a symbol we use for the speed of light. Now is where you see the power of scientific notation, because without a calculator I can solve this. How? Because this is all multiplication. This is multiplied by this, 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 and multiplication can be rearranged as long as it's just multiplication, right? I can rearrange it any way I want. So in particular, I'd like to multiply these two numbers first. 3 times 3 is
9.
done. 9, you all know. Right? Now I want to multiply these numbers. 10 to the 8 times 10 to the 7 is
15.
10 to the 15. You can do that very rapidly by thinking about the logarithmic counting, right? It's like I went up 8 generations, and then I had to go 7 more. Right? I multiplied 10 to the 8 by 10 to the 7. If it had been negative, I would have been multiplying up and then going the other way, right? And then I would have subtracted. So when you multiply 10 to any power times another number, 10 to another power, you add the exponents because we're logarithmically counting. That's the advantage of logarithmic counting. So I get 9 times 10 to the 15. Now I can take the meters per second, multiply by the second. What do I get?
Meter.
Just meters, because the second is on the bottom, the second is on the top, and they cancel. I just get meters. I just answered the question. That's how long a light year is.
So you took a second because it was in the top and the bottom. So it counts on.
Exactly. This second is in the denominator. This second is in the numerator. They cancel. Right? A divided by A is 1. That's an extremely powerful thing I just did, right? Because just by looking at the definition and knowing a little fact, how many seconds are in a year, and knowing the speed of light, I just multiply these two things together and I get how far a light year is. This is an incredibly far distance. It's not even the distance to the next nearest star, but it's still an incredibly far distance. It's so big, like think about this, this is 15. We went up to 12, and that was a trillion. 15? What do you call that? Some people call it a quadrillion. It's a ridiculous number. No, we don't have English words for them as they get bigger and bigger. They're just absolutely enormous things. 15 generations of rabbits producing 10 rabbits each time. It's so many rabbits that the Earth's covered in rabbit, right? It's an enormous amount. And yet we need to be able to think about it because those are the actual distances we measure in the context of this course. Great. I'm going to do one more thing. Remember I asked about if anyone had ever seen a million of anything? I'm going to ask a slightly different question. Let's imagine that I had a cubic meter. What do I mean by a cubic meter? You all know what a meter is. A meter is about that long, right? Imagine you had a square meter and then it was sort of raised up by another meter. So something, about this big. You could fit in. You could probably,
Like a three-dimensional.
Three-dimensional, right? Like it was a box about this big. And you could sit in that box. Turns out our volume, this is a measurement of volume, is about half a cubic meter. Most people are about half a cubic meter. So you could probably fit 2 people in this box, but it's a a decent sized box. Not much larger than half this table, right? Maybe about the same size as half this table. That's a cubic meter. 1 cubic meter. That's how we write cubic meter, right? That's my drawing of a cubic meter. Imagine that it's sitting there. Now I want you to imagine different volume. We had talked about a centimeter before. Now imagine a cubic centimeter. Right? That's 1 centimeter on each side in 3D. A little tiny little thing. 1 centimeter by 1 centimeter by 1 centimeter. Something you could fit easily in your hand. Right? It just sits right there in your hand. You've got this box that's a cubic meter. You've got another box that's a cubic centimeter. The question is, how many of those cubic centimeters fit in the box? Cubic meter box. How many?
100.
A million?
Well, we got all kinds of numbers throwing around.
100.
100 seems like it makes some sense. Let's see if we can solve this. The key here is that these 3's are important. And the other thing that's important, and I'm sorry that this is the case, is that that cube doesn't just come along the ride for the m, it also comes along the ride for the c. It's centimeter cubed. The meter is cubed, but the centi is also cubed. Yeah? So let's do the game that I was talking about before. We'll start with 1. What is a centi?
100. It is 100.
10 to the?
-2.
-2. So I'm going to have 10 to the -2, and I have a meter. It's just multiplied by. But that whole thing is raised to the 3rd power. That's the same thing. It doesn't look like it, but it is the same thing as a cubic centimeter. Looks complicated, but it gets simpler.
How you got 10?
How do I know it's 10 to the -2? Because the definition of centi
Okay.
is 10 to the -2. That's what it means. So if I take this 10 to the -2 and I raise it to the 3rd power, and I take this meter and I raise it to the 3rd power, you may recall that exponents have to distribute into multiplication. Do you remember that? You can prove that to yourself by doing some simple problems, like if you take 10 squared times 10 squared and you square all of that, and then you see what the answer is, you'll see that, oh yeah, I have to distribute these numbers in. They have to, this number has to come in here and it has to come in here. It has to be raising both things. Right? That's different than multiplication. Exponentiation is a level up. How do I exponentiate an exponent? What happens?
6, -6.
That's right, you multiply. Why is that? Well, let's look again. Let's imagine this. I have 10 to the 2, and I'm going to raise it to the, let's say, the 4. Right? What does that really mean? That means I have 4 10 to the 2's multiplied by each other. 10 to the 2 times 10 to the 2 times 10 to the 2 times 10 to the 2. Right? I add exponents. So 2 plus 2 plus 2 plus 2 is what? 8. So you see what happened? The idea of exponentiation means that I'm multiplying many, many times. That's the same thing as multiplying in my logarithmic counting ideas. These rules are explained in your textbook. You've learned them before. But it's important to kind of get a sense for why they work. Because it's the concepts that are important. It's not so much whether you remember this rule or that rule. If you mess up and don't forget, that's not as important as knowing why I have to raise both things. Right? But I do. And also why, when I raise an exponent to another power, I multiply. So if I do that, I have 1 times 10 to the -2 cubed. And then there's a meter cubed here. So what's -2 times 3?
6.
-6.
-6.
A negative times a negative is positive.
Correct, but this isn't a -3. It's a positive 3.
Oh, sorry, I see the little multiplication.
Yeah, I'm sorry. That's a dot,
Sorry.
not a multiply. Yeah, it's not a. But you would be right if it was -3. Meter cubed. That is what a cubic centimeter is. Just like what we did before with a centimeter, that is what a cubic centimeter is. But we want to know how many cubic centimeters fit into a cubic meter. So we want to do the same thing we did before. Right? We want to get cubic meter on one side this time instead of cubic centimeter. So what do? How do I get this to just say 1 cubic meter? What do I have to divide by? Divide by this number,
Yeah.
right? 1 times 10 to the -6. 1 times 10 to the -6. When I divide by a negative exponent, what happens? Comes up to the top and becomes a positive exponent. Right? It's the same thing as division is the opposite of multiplication. Addition is the opposite of subtraction. It's the same idea. So if I bring this back up, it becomes 1 times 10 to the 6 cubic centimeters is equal to a cubic meter. So whoever said 1 million cubic centimeters was correct. So remember when I said, have you ever seen a million of anything? Well, if you've seen a box that was this size, you've seen a million cubic centimeters. It's sort of surprising that you fit a million cubic centimeters in something like that. You know, just a million. These are not incredibly tiny things, but a million of them fit into one box. Sort of of surprising. This is the power of this sort of form of mathematics. You know, no calculator was necessary, right? I just needed to know a few of the terminology. That's all I needed to do. And maybe I needed to know a couple small facts. To be honest, I will always give you those facts or give you the ability to look them up. I'm not interested in you memorizing formula. I'm not interested in you memorizing or doing very complicated mathematics. Although you'll find that the mathematics, a lot of mathematics becomes very easy to reduce to easier mathematics as long as you're able to make these estimations, as long as you're able to make simplifications like this. But this is the sort of thing that we're asking you to do in your homework. This is the type of homework question that we're going to be looking at. And we'll have some opportunity to do things like this in groups next class when we meet. Are there any questions about this? Okay. Let's take a 10-minute break. There's a lot of math, so we should take some break.